Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks. I want to start by thanking Eric for this fantastic, engaging talk where he outlined the enormous progress we, as an AI research community, have made over the past decades, and also looked at the challenges that are still ahead of us, especially as we develop AI technology that will drive collaborative system of the future, where humans and AI can really work together to solve the really hard problems that we have in the world today. In the next talk, I want to look at Project Malmo, and this is one of the initiatives that we take to enable that research moving forward. I want to argue that a lot of this research can happen first in virtual environments before we start to push towards solutions that can deal with the complexity and unpredictability of the real world. Project Malmo is such a virtual platform. It's based on the game Minecraft, and we have released this as open source for all researchers to use over the coming years. We're very excited to be putting this out into the world, and we're very excited to see what people will come up with. So let me start by just giving a very brief overview of what motivated Project Malmo. The starting point was the dramatic progress we have seen in AI over the past couple of years. As you have seen, there have been dramatic progresses, especially by progress in the area called deep learning. For example, today we have speech recognition systems of human-level accuracy that drive already important applications such as Skype translators, where people can go in and use real-time speech recognition and machine translation to communicate with someone who doesn't speak their language. So we're already starting to use technology to break down barriers between people. You already saw the exciting work on image captioning and how that can enable assistive technology, for example, helping the visually impaired community to move around in real spaces. So looking at some of those dramatic advances, some people are starting to speculate and say, well, we're so close to solving AI, it's really just a matter of scaling things out and up. And if you really look closely, that is not true at all. And I just want to very briefly give a sense of what the challenges are that are still ahead of us. One specific challenge that I would like to point out is that the systems that we have developed so far are all very custom targeted at a very narrow application. So we can use huge amount of human ingenuity and engineering resources to develop AI systems that address a single narrow task. And in those single narrow tasks, those systems can become very, very sophisticated and very, very useful, such as in the applications that you already see. But when we talk about artificial intelligence, what we would really like to see is something that can much more broadly and meaningfully interact with the real world. If you think about the intelligence we see in nature, if you think about a newborn child, what distinguishes their cognitive ability from what we have in artificial systems today, there's just no comparison. It's a completely different thing. So it's not even clear to me that we should be talking about intelligent systems at all. But if you look at a child over the course of their lifetime, they can learn to do a huge variety of tasks. They can learn the language of their parents and the community around them. They learn to meaningfully interact with people around them. And they learn over time to do hundreds and hundreds of different things that they need to survive and meaningfully relate to the real world around them. In terms of technology, we are very, very far away from this. But we are hoping that over the next years or decades, we can start to address some of those challenges. And addressing this would allow us to develop systems that more genuinely interact with the real world, that aren't put off, that don't break when they come into an unpredictable situation, such as Eric's Tesla, for example, and that can more genuinely adapt to the world around them. So just to highlight two of the key OpenAI challenges that have motivated our work here, the first that I would like to highlight is this ability to flexibly learn across tasks, to learn something new as you come along and as you encounter challenges in some complex environment. So the goal here is really, or the limitation at the moment here is that current AI technology can perform at a very high level of sophistication, but only at very specific, very narrow tasks. For example, only at a very narrowly defined aspect of object recognition. Now, the research challenge is, how do we develop AI systems that learn to perform a wide range of tasks? And I've already mentioned that we're using the game Minecraft as an environment for pushing technology in this direction. So you could think about how to develop agents that learn how to navigate around obstacles and avoid falling into lava or encountering other dangerous situations. We could look at how to navigate some complex environment in climbing hills, or how to construct new things, how to use the resources in the environment to craft, for example, a crafting table in the game, which would allow you to make more sophisticated items like pickaxes and other items that you might need to construct something in this particular environment. Another premier challenge is learning to collaborate. So if you are in a complex environment with other agents, and ideally in the long term we want to work towards environments where AI and humans can genuinely collaborate with each other and complement each other, then you need some shared understanding of the space. Current AI has very little understanding, or very little genuine understanding, of their human users, their goals, and how the AI system could go and support the user's goals. So a challenge here is to understand how we could develop AI that understands the user's goals, what they're trying to do, and how they could help come in and really make a contribution to the task that the human user is trying to achieve. So in the example over here, there's a mock-up of how an AI agent could help to, for example, collect resources to help a human construct a house in Minecraft. Now, what are we doing to kind of start to even think about how we can address those challenges? I would like to introduce the Malmo Platform for AI experimentation that we have developed and that we think can really enable some of this research in pushing forward fundamental AI research. Why have we chosen Minecraft as the foundation for this platform? Let me see who in the room here has played Minecraft before, just to give me a sense of what we have here. That is slightly less than half. So if you are not familiar with Minecraft, oh yeah, that's a very good one. Whose kids have played Minecraft? Roughly this. There's some overlap, but there's okay. So that looks like roughly half of the people here kind of know what the game is about. So let me just very briefly give you an idea for those who aren't very familiar with it. So what's appealing to kids about Minecraft is that it's this completely open-ended world. You can go in there and have adventures with your friends. It's very social and collaborative. So here, for example, there's a Minecraft player just exploring this world and trying to see what is out there. And if we talk to 1,000 Minecraft players, they come up with 1,000 different ways of playing the game. And that, to me, makes the game very useful for the kind of AI research that we want to enable. Because in Minecraft as the game, there's no way of winning the game. There's no sense of, oh, I just want to reach this maximum score. So this opens up this possibility of focusing on research that can help us develop agents that flexibly learn new tasks as they go along, and to ideally push this towards technology that can do lifelong learning and pick up new skills as they interact with the world. So first, what Minecraft enables is this infinite variety of tasks that we can put in front of AI agents. The worlds in Minecraft are procedurally generated 3D worlds that both human and AI players would experience from a first-person perspective, very similar to how we experience the real world, but in, of course, a simplified form. And I think this combination of just simplifying the problem enough to start to get a handle on it, together with this huge flexibility, creates a really interesting space for experimentation that can really push the state-of-the-art forward. Now, what have we done with the Malmo platform? Malmo platform is, let me just see how to, oh, is this playing? Yeah. The Malmo platform consists of a mod, so a plugin into the Minecraft game that exposes the internal state of the game to our platform and through that to the AI researcher. And it also allows agents to be hooked into the game to send commands to this environment. So we are providing this mod, an intuitive API for getting agents to interact with this environment, and a set of tools that is designed to make it easy for researchers to go in and focus on implementing their AI agents and setting up experiments as quickly as possible. So researchers can now easily experiment with existing tasks or define their own using a simple XML format or scripts to generate a wide variety of tasks for their agents. It's possible to overclock the game, so people can collect data at a much faster rate than would be possible in a real-life system. And we see here in this video just an example of an agent interacting with the environment and the data coming into the system in real time. This can include different kinds of observations, including just the pixel observation of what the agent can see, as well as internals of the state of the world, where the player is in the world, etc. The agents are embodied, so they really experience the world in a way that is much more like a real world experience than something that, for example, just has a top-down view of a 2D scene. The environment is very complex and dynamic, and we're very exciting to now have this ability to also support multiple agents within the same environment. So this really starts to allow us to develop systems where an AI agent and a human user would need to collaborate within this environment to address complex tasks. And this allows us to focus on this line of work where agents, human agents and AI agents interact with each other. We have the ability to collect human training data, and this also allows us to learn from interaction with real human players. Just as one example of how a human and an AI agent could be interacting within the same environment. So here we have the AI agent view on the left. It's trying to navigate to this red goal there in the back. And the human with the view on the right can help the agent to navigate to the goal. And of course, in the long run, we want to also have AI that can help humans to achieve whatever goal it is that they are trying to achieve. Just to give you a very brief overview of what the platform is, and Tim will later on give you much more detailed ideas of how easy it is to go into the platform, implement an agent, and run a first set of experiments. But just as a brief overview to get you started, we hook our mod into the game Minecraft, as I already mentioned. And this mod runs within the Minecraft process and exposes the state of the world through observations and rewards. And it listens to commands that are sent from the agent. So on the agent side, you essentially implement this loop where you get some observation from the environment. You may get some reward signal that tells the agent whether it's doing well or not so well, whether it needs to improve its performance. And then it sends back commands to interact with the world and have some effect on the environment. I'm very pleased to announce that Project Malmo has been open sourced just a week ago. We are already seeing a very enthusiastic community spring up around the platform. It's available on GitHub, so if you're interested, go and try it out today. I don't know how much time I have left. 15 minutes? Okay, so that gives me a little bit of time to just give you one intuition or one kind of approach that I'm very excited about working with this platform. So very generally, I've talked a lot about AI in general, and there are many different kinds of approaches that people have worked with. One type of approach that is very promising is called reinforcement learning. And reinforcement learning is really about learning from interaction with the environment, so learning from trial and error and learning about the environment as you go along. In reinforcement learning, interactive learning is, as I mentioned, modeled as learning from trial and error. So its simplified view is of an agent that interacts with some environment. It can observe some state that the environment is in, can take some action in response to the state of the world, and then it observes some reward signal that it is trying to optimize. This kind of approach very naturally fits in with the Malmo experimentation platform. So for example, in some of our work and some of the examples that are also provided with the platform, we show how reinforcement learning can be used to train agents to, for example, navigate to a goal in Minecraft. So for example, if you look at an arena top-down view, you could have an agent that starts down here. It has to navigate some obstacles and it has to get to the goal. without being told ahead of time what it is supposed to do. So it really has to go out, interact with the world, and figure out what it is that it needs to do. Typical approaches for this are based on, for example, temporal difference methods, where the agent estimates the state of the value of the state that it is currently in, and the value of taking some actions in that state. And this can be done by propagating backwards in time the experience that the agent is collecting. Just to illustrate this, I want to show one demo that is an example that we provide together with the platform. And this is just implementing a classic approach to reinforcement learning that is called tabular Q learning. So in case you're not familiar with this, let me just see if this is a maze that the agent can actually solve. Yeah. In case you're not familiar with reinforcement learning and in particular tabular Q learning, in this particular example, we can see a representation of the world as the agent sees it. So all the agent observes is the number of the state that it is currently in, and it knows that it has 4 actions available, so moving north, east, west, or south. And it has to learn from trial and error what the consequences are of taking a certain action in that particular part of the world. And so you can see over time as it goes along, the green kind of areas here indicate that the agent has found that taking this action in the state is either neutral or a positive, or resulted in a positive experience. And when you see those red ones over here, it observed negative reward. So it has learned that taking this particular action in that part of the world leads to negative consequences. And over here, you can just see the visual representation of this, which in this case is just for us to get an understanding of what exactly is going on. The goal is eventually to figure out how to get to this blue square in the back. And only when the agent actually reaches this, it would observe this positive signal, hey, something good happened. And then it can start to learn how to propagate this back through its state space to reliably get to the goal. Of course, approaches like tabular Q learning are very basic, classic examples of how reinforcement learning works. But we have seen in the recent literature that this concept of learning from trial and error, when coupled with, for example, deep learning, so automatically learning a representation of what's going on in a visual scene, can together create very, very powerful approaches for learning interactively in interaction with the real world and making sense of someone's environment. In the examples here, I'm showing 2 videos of agents that we have trained through a combination of imitation and deep reinforcement learning. The idea here is that if the agent has to just learn from trial and error without knowing anything ahead of time about the task that it's trained to do, it requires a lot of exploration. So you have seen that in the tabular Q learning example, the agent has to move randomly a lot before it can get some idea of what it is that it needs to achieve in order to get positive reward. Instead, we can bootstrap an agent from observing someone else's behavior, for example, observing how a human player would navigate to the goal. And then starting from there, the agents can learn much more quickly of how they need to adapt their behavior to the particular task ahead of them. So these types of approaches are very promising, and we're looking forward to having more research that is inspired by putting this platform out there. I just want to end with noting a few opportunities for interdisciplinary research. So there is a lot of research activity now in core AI, in scaling up reinforcement learning and machine learning methods to deal with complex scenarios. But I think there's a lot of research potential for work that needs to happen in order to finally develop systems that are scalable and robust and meaningfully work in the real world. For example, there's a lot of space for interaction between hardware designers and AI researchers. For example, to understand what compute platforms we need to build to deal with the complexity of the learning mechanisms that we eventually want to put out in the world. There's a lot of space for systems and networking research in collaboration with AI research. For example, to understand how to manage complex AI architectures and pushing through the huge amounts of data that we eventually want those systems to deal with. There are very exciting challenges in the area of AI and programming languages, looking at how we will code, how we will develop the AI agents of the future. And finally, there's some very exciting challenges in terms of user experience. So how will we design AI systems that can meaningfully interact with human users? How can we design systems that can take feedback from people and that any person can teach to do what it is that they want to achieve, rather than having someone, or rather than requiring someone who is an expert in machine learning to get those agents to do what they want. Because we're in such an interdisciplinary kind of workshop today, it would be great to have some more discussion on those particular aspects and understanding how different disciplines can contribute to push research forward. To summarize, I have given a very brief overview of recent advances in machine learning and outstanding challenges in AI research that have motivated our work on Project Malmo. We're today proud to announce that we have developed Project Malmo as an AI experimentation platform on top of the game Minecraft. We're very excited about the research that this will enable, and we're looking forward to hearing back from you about the platform and have you try it out. Thank you so much for your attention.
Thank you. Are there questions, comments? Okay.
So what aspects of, for want of a better word, I'll call it the real world,
Sure.
do you think that you are able to capture usefully in Minecraft, and what aspects do you feel you're really not able to model?
Mm-hmm. That's a fantastic question. Thank you. Let me start with the limitations. So Project Malmo is not designed to be obviously a replacement for the real world. There is a coherent physics in Minecraft. There's a lot of complexity, but it's nowhere near what real world physics would be like. It's nowhere near the complexity of the real world. So we think that by just pushing on the complexity and realism in the right direction, we're hoping to create this spot between what we can do using current kind of evaluation platforms and eventually moving to the real world. So the hope is that by making it very quick and very easy to do experiments here, we can make progress on the, for example, learning mechanisms that would be required to deal with complexity and unpredictability. Once we get new insights there, we can then push those out and have to, of course, fine-tune them for realistic scenarios in the real world.
My name is Dapeng Oliver Wu from University of Florida. It's a very good talk. So regarding the more general AI, I have a question about this fundamental problem, that is, can we develop a computer that is able to create methods of methods, which means that we're not looking at a specific task. Mm-hmm. We're looking at whatever problem you give me, I first create a general method, and then the general method will tailor down to a specific way to solve a specific problem. Mm-hmm. So human has that capability that is able to, so when I learn mathematics, I learn how to solve mathematical problem, right. And then later on use the same strategy to solve physics problem. Mm-hmm. So this kind of capability seems to me is not there in AI.
Right. So that's a very interesting question, and I interpret that as relating to the ability to abstract, to form more general solutions to a variety of problems that someone has encountered in the past. It's very much an open problem in the AI or learning community, how to achieve this. And we are seeing some interesting insights into, for example, how to transfer knowledge from one task to another, how to learn reusable skills, or in reinforcement learning, there's something called options that could be applied to many different scenarios. So people are starting to look at this ability to automatically learn abstractions from interaction in complex tasks. But I think that in the past, a lot of the tasks we put to those learning systems were not quite complex enough, weren't quite coherent enough, didn't require enough common sense knowledge, as you will, to really push the systems in that direction. So I'm very excited about the opportunities that we have with providing those more complex tasks in this environment, and hopefully make some progress in this ability of agents to form abstractions and generalize to new tasks.
Hi, I'm Adam Yal from MIT. My question's kind of more of a technical detail. So you mentioned that you could speed up the game 50x to more rapidly acquire experience for training models, etc. In your experience, is that sufficient for things like DQN approaches where you require an order of like tens of thousands of episodes to really start learning something interesting? Can the platform move fast enough to enable that kind of method?
Right. Very good question. It depends a lot on the back of the envelope calculations of how much data your approach is going to need. It's certainly enough to really have pushed us already in the direction where the amount of data that we can collect is interesting enough and substantial enough to address tasks. What's interesting to note here is that because researchers can create tasks at exactly the scale and complexity that they need to understand specific questions in terms of their AI approach, you can kind of work out how complex your task needs to be, how much data you require, and you can reason back to understand what exactly the experimental setup should be. So it's very flexible in this way, and it's a very powerful way to quickly iterate on a specific method.
I'm going to try a slightly more nuanced version of my question, which is there has been a history. I mean, you showed a reinforcement learning task, and I think, you know, back to Wumpus World, which is maybe before you were born, but there's been a history of these you know, game simulation things, from Wumpus World to Unreal Engine to various things with The Sims and Civilization, now Minecraft. And so maybe I'll put the question like this. In this history of, I'll call them gaming environments, what advance does this gaming environment for running my AI, reinforcement learning, or other tasks have over previous existing ones?
All right, let me try again and see if I can answer the question better. I think throughout the history of AI, there, as you mentioned, have been a lot of examples of game environments and other abstract scenarios that allow researchers to really push on specific questions. So you mentioned civilization. Something like this can really be used to push, for example, on planning approaches that require some information about what the state of the world is, and then you can do planning there. Same chess, Go, backgammon, they all have done, they have provided a fantastic platform for pushing the state of the art in very specific directions. What I think is new here is this flexibility that you can create arbitrary new tasks within the same coherent world virtual environment. So we can now create tasks that require to walk an agent from A to B. We, let's say, develop an approach that we speculate can generalize to other tasks in a rather flexible manner. Then as a researcher, we can come up with a new set of tasks, 20 that require the agent to do some kind of building that puts it into a completely different part of the world that looks very different from what it's seen before. And then we can start to test whether we have correctly developed a system that can generalize to new unexpected situations. And I think in the past, it was often possible to optimize for one specific type of task, and it's pushed, or it's held approaches kind of focused on the narrow AI scenarios. And I'm hoping that with this, with, for example, crowdsourcing a huge variety of different tasks for the agents to do, we can push towards this greater flexibility. But if you're not satisfied with that answer, I'm very happy to take it offline and
Okay, I'll
talk
take
more
the
about this.
last question. Well, you'll take it rather.
Thanks. Ron Parr, Duke University again. So I want to, maybe this is a better question for later, but I was curious about what the state looks like to the learning agent, and is sort of related to that, I was wondering, is it, depending upon how you answer that question, I'd ask, is it really a POMDP? And then also, are you creating a very difficult perception problem that's maybe more difficult than it needs to be because you picked Minecraft?
Okay, that's a fantastic set of questions. So let me start from the observations. The platform we have built is very flexible in the way that you can plug and play the kinds of observations that you want the agent to receive, as well as the action space. So depending on the approaches that you want to work on, you could provide a more symbolic representation of the world, at least locally. You know, what is the block structure that exactly is around the agent, what items are there, and this would allow you to do, for example, look at approaches that do planning using a reasonably known model of the environment. You could provide something that is representative of, for example, robotic sensors. For example, we provide depth images of the environment, as well as just the pixel image of what would a camera mounted on top of the robot see in this environment. So you can work both with individual sensors or with combinations of those. And because the platform is extensible, we're also inviting people to put in other forms of observations that they think would be useful to work with in that particular environment. And this again creates some very interesting opportunities for figuring out what sensors might be needed to work in something, you know, that eventually moves towards the real world. The POMDP, there's a lot of partial observability there. Depending on how you construct the observations, it may or may not be an MDP. We have already noticed that the assumptions of, for example, discrete time steps breaks down quite quickly when you try to address the full problem of navigating in Minecraft. There are a lot of things that the abstractions that we typically use don't capture quite well, and I'm very happy to follow up on that offline.
All right. Well, thank you very much, and I'm sure we'll have more discussions on the details here. But just before I let you go, Katja, so what would you say today the audience is for Project Malmo? Here we have professors who are both researchers, educators. Do you have to be an expert in RL,
Right.
DL? I mean, you know, what today?
Right. That's a fantastic question. We designed the platform with AI researchers in mind, but the moment we put it out and made it publicly available, we noticed that it was also appealing to different audiences, all the way to, for example, enthusiastic high school students who know a little bit of coding, have maybe done a few coding exercises in Python, but they're very excited about Minecraft, and they were able to come in, go through our tutorials, and get started in playing around with some of the agents that we have here. So the barrier to entry is actually very low, so invite everyone to go and play with it. Of course, the opportunities are quite wide open in terms of the sophistications of the agents that you can eventually develop there.
All right, thank you very much, Katja.
Thank you.